way to solve it has been to go bigger. We wanted to challenge ourselves and we designed especially for underserved languages. The problem is that better performance for underserved languages. Small LLM that performs well on multilingual tasks, 70 languages, balanced multilingual model, not being run on your phone. Today I will talk about all the different pipelines, how we got here. Can everybody hear me okay? Okay, cool. So today I'm going to be talking about Tiny Lambda. It's our latest tiny module is the 3.35 multilingual dense LLM. It supports 70 languages. So I'll talk a little bit about the problem that we set to solve, and then I will go back to the details. But basically, multilingual progress has been new, and the main way to solve it has been to go bigger. We wanted to challenge ourselves and ask this question: can we design a small LLM that performs well on multilingual tasks, especially for underserved languages? So if you look at this chart here, way over on the right is the language cluster of African languages. And you could see, compared to Gemma, we have better performance, and this is what we designed for. But like, as you go away in terms of resources or servedness, the quality of the language model really goes up. Right? So we wanted to challenge ourselves and see if we could design for this, where we get better performance for underserved languages. So our main hypothesis for this model is that if you want balanced multilingual performance at a small scale, it's a design choice. You need to make the right choices at each stage of your training pipeline to be able to achieve a balanced multilingual model, not one which is not just good at benchmarks or benchmarks, but is also good to chat with, has been generated quality, can translate well, and can run on your phone or on your laptop. So I talked a little bit about what we released. We released 5 models as a research release. They are all 3.35 billion parameter. We covered over 70 languages in this. There's a tech report, a release on archive that actually just landed today. A demo, and then a way to run this on your phone. So today I will talk about all the different pipelines. So our pre-training stage, post-training stage, how we evaluated the model, and then finally what we did for quantization to get this running for the laptops. I'll also conclude looking back on the IR model series and how we ended up here, and also talk a little bit about how we think about doing research and how we got here. How about 3 to 4 years worth of projects currently in timeline. Okay, on to the technical bits. So for pre-training, this is the foundation. An analogy that I've heard and that I like is if your final LLM is a dish that you serve to your users, pre-training is fun. It's where you get the vegetables that make up the ingredients for the final dish that you're going to serve. So everything is downstream from the quality of the vegetables. It takes a long time, and you get to do it maybe once or twice, not more than that in a span of 40 months. First things first, to make a sensible design choice for multilinguality, you need to be thinking about the tokenizer. The problem is that standard tokenizers sampled from the data distribution uniformly, and high-resource languages will be overrepresented. This basically means that lower resource languages or languages that have unique representations in Unicode have more tokens per word, and sometimes even the individual tokens don't make choruses. This results in slower inference, worse strings, worse learning signal, and basic capacity in year 1. So we address this with 3 solutions. One is that we decided to use one single tokenizer that covers all the languages that we care about. This allows us to flexibly post-train, flexibly merge, flexibly use these models for inference. So this was a key finding from one of the papers from our lab, one tokenizer to do it up. The other thing we did is we have a very large vocabulary size. Our vocabulary size is 260,000 tokens. And this basically comes from the fact that you need a large vocabulary to be able to represent lots of languages. And we used a unique weighting scheme, which I will talk a little bit about, where we not only follow the data distribution on which we're training our tokenizer, we group languages based on family or script. And then we give them additional weight based on this. So this allows underserved or underrepresented languages in the training data to be able to get more. For technical detail, we train our tokenizer on FindWeb2, 50 gigabytes of that, and we use GPT 4.1s or GPT 4.0 like X without normalization. And you can see that in terms of token efficiency, where even for languages like Telugu, Gujarati, where the tokenization efficiency of models like 12x smaller than is architect, we are in green, and this is sorted by how efficient you are. We have really good tokenization efficiency, though these models are quite underrepresented in the training. Okay, now moving a little bit on to the pre-training data. We pre-train this model in 6 trillion tokens that covers 70 different languages. The majority of the training corpus is publicly available common for all data sets. Some proprietary data that covers these 70 languages and includes code data. Our previous research from lab has found that including code data not only is important for code, but also helps in reasoning and natural language. We balance the language proportionality similar to how we do the weighting in the tokenization stage. So we use the natural distribution, but also use the family script bucketing to be able to equally or sort of more equitably balance the languages we include. Finally, we have a quality pipeline. So we use a bunch of heuristics, so things like language ID, stop word filtering, reunification, and then most importantly, we classify documents into different domains and have trained classifiers that tell us the quality of these documents. So we can filter them out, upgrade them, not yet. Finally, the last stage in our pre-training is a cool-down phase, where we have a bunch of sort of high-quality data sets, instruction-style data sets, math, science, and we do cool down on this. This is similar to small LLM, but with a focus on being multilingual and houses languages. Now I'll talk a little bit about the architecture. So this is a 3.35 billion dense efficient architecture that is designed to be deployable in small scenarios and be very efficient in inference. Our 4 key things that we lean on is we do parallel transformer blocks. So we parallelize the computation between the attention blocks and the FFP. We use an interlinked attention with a 3:1 ratio between sliding windows and global attention. We use no positional embeddings for the global attention and for the sliding window attention. We use six video activations without bias, this is streaming stability, and we use GQA with a ratio of 4 KB and share 50.560 megabytes. This is similar to our command A model architecture, and Sebastian Dashka has a blog post that actually uses this architecture. I think the parallel transformer block is not very commonly used or not very used. So to summarize our pre-training recipe itself, 6 shipping tokens, we use 256 H100s. We use a warm-ups stable decay schedule, and we get the hyperparameters for these by doing computations at 200 billion token parameter count, and we could pull down numbers for 40 billion. So we find a hyperparameter data mix between the short training runs, and then we can one training time for our system. We use FP8 training with mixed precision. We keep the things that are important in that position, and this is mostly for training. We use a JAX-based framework to train it. So to summarize, we have a single balanced tokenizer where we made the decision to have equal treatment for 70 languages, 6 trillion tokens that we've trained on, a dense 3.35D architecture, FP8 training, and then video versions and 1 tokens. So now we have our base model, which is our raw ingredients to make dishes. And post-training is like cooking and experiment. You can do lots of dishes before you decide on defining what. So I'll talk a little bit about the data, which is sort of how we took the model. I'll talk a little bit about merging, and I'll talk a little bit about synthetic data. Okay, so for multilingual, there is a dearth of data for the vast majority of the languages. So what is straightforward and is done is you collect high quality English data sets and you translate. And that's good enough first effort, but we found that if you can extend this multilingual coverage via multi-stage synthetic pipeline, you get much, much better results. So our synthetic data pipeline is language specific, data set specific, reproducible, and applicable to information. So if anyone's wondering, like, how do I generate data? What's the best way for me to be able to leverage the existing data that I have for other languages or other uses? This sort of pipeline is generalized. It's not just for this use. So what we do is we take our source data sets, we design, we translate them using different models, and I'll talk to you a bit about how we select the models and stuff. Once the translation is done, we look at the prompt. We say, is the prompt of a sufficient enough quality? And if it is, okay, great. We continue translating the response. If it's not, we go through a multi-stage pipeline. The first thing that we do is what we do call prompt transformations. So we can change the prompt to be more appropriate for the language that we're translating. There's 3 transformations that we do here. After that, we move improvement on best of n. Best of n is where we have multiple models that are generating your synthetic data, and you pick one. We do an improvement on that called fusion of n, where we take all the generated samples, have a fuser that fuses and combines these different responses, and then k. And so that gives us our final sort of multilingual SFT data set. Right? So for translation, we use command A translate and UCD3. We hold out their sets for all the languages, and we estimate the quality of the model using AFICOM and XY Excel. And based on this, we decide to use command A translate for Canada and maybe deep signal for French. Now, I talked about the prompt level transformations. We do 3 transformations: naturalness, cultural adaptation, and difficulty enhancement. So when you translate, there's often this notion of translation is like sync or So for naturalness, we remove this translation. So as an example, I don't know if this is very visible at the back, but the same prompt here is saying what is traditionally served with turkey and Thanksgiving. And when you translate it immediately in German, Thanksgiving still remains as an English word. So the naturalness transformation takes that Thanksgiving word and translates it to the German version, which roughly translates to Thanksgiving. After that, for cultural adaptation, Thanksgiving might not be the festival that's celebrated in Germany. So you replace that with Christmas. So what is traditionally served in Christmas? And then the difficulty is just making this more complex. So instead of asking what is traditionally served for Christmas, you could ask what should my shopping list be for served Christmas Day? And so that's a difficulty or a complexification part transformations. And we find that this results in not just more fluent, diverse, and better completions, but even the model trained on it downstream has much better generative quality for the language. Okay, now you have the prompt level transformations where we're looking at actually generating the responses to these prompts. So in fusion of n, you have multiple different models generating completions for a given task. And with this prompt, with these completions, we have a fuser model that sits on top and incorporates elements for each different generation. So this allows you to make use of all the different generations you've done. And a common question might be, if I'm using the same fuser as one of my generations, how is it any better? You get better diversity, you get higher levels of language matching, language fluency, and we have a paper on this called Making, Not Taking the Best of N, that you really has mentioned. Finally, in the post-training data for SFT, we also have a quota of multilingual translation. So MT for cross-lingual transfer. Here, Our data pipeline is slightly different because translation is a very specific use case. So we have rubric screening, language identification, and then quality estimation. So to understand the difficulty of whether a given prompt or sentence is how the translator will go, we have this quality estimation to see if it's just broken sections that cannot be translated. Then we do a difficulty estimation, and then we do back translation. This allows us to have a corpora of corpora for 98 languages. We keep the 98 languages as is for cross-enable transfer. There was a model release last year called Command Translate that specifically built upon this, and so we use that release. So now we have 70 languages, and we are a very small world. So you can, of course, try and fit all of these into one, which we do. But also you can train good models for clusters that people might be interested. So we split the 70 languages into 5 regional clusters: Asia Pacific, Africa, South Asia, Europe, and West Asia. And we group these into training clusters. So we take the 5 regions, we group them into 4 training clusters, the ones that we've seen. Across these different training clusters, English data and code data is common across them. And this is also crucial. Keeping your English data is very important for maintaining historical performance. English provides a lot of the knowledge and facts that the model gets. And so if you go too low on your English proportions, your model quality is not good. So we make out of this, we make 4 models, 3 for the group regions and 1 with all the regions. So if you're interested, this is what our sort of data proportions look like. So you can see there is English and core, which is the beginning sort of bars here, and core is at the end. And then the proportions of the various other clusters in the mix are in. And the reason you might ask is like, why am I including South Asian cluster when I'm training a Europe West Africa model? Is the model has forgetting, and to prevent this forgetting, we include these small amount of data to sort of act as a regularization and not cause it to forget or if it wants on these. Okay, so what does the recipe look like? So for SFE, we use 16 H100s. These run in about 24 hours. We check for 3 blocks and have a bunch of hypers. We curate the data mix and the hypers on a test set where we build up evals for certain regions. So we not only look at average performance, we look at minimal performance and sort of comprehensive evals. Finally, we do apply gaming, but very little, not a lot. And this is a design choice. We intended this model to be a research piece to be used by the community. And on common refrain that we hear is that if a model is running at a reference to queue, it's hard to further SFT or to do a reference tuning on top of that model. So we did a very PGO alpha that basically teaches the model its name, what language it knows, and to maintain multilingual. So we kept it small also to prevent sort of catastrophic forgetting that you get when you push the model very hard at you. Okay. I talked a little bit about model merging as well. We found this to be a very cheap, powerful tool. So what happens is when you do these region-specific SFTs with our 4 or 3 clusters, the model loses capabilities like instruction following, it starts to forget knowledge that it had from before, and it loses some safety. So we found that merging the region-specific models back with the global model works really well in sort of preserving all these recipes on all these quality different activities. We use a method called SimMerge, which allows you to sort of in a very cheap way decide which merging method is best, what order to merge your check answer. And there's no label data needed for this. You can just have to go on to forward process. You can be able to decide on the merge. Okay. To summarize this training, we have a synthetic data pipeline which does translation, prompt transformation, and thus fusion multi-teacher synthesis. We also have a translation data corpora covering 98 languages that we leverage. We do 4 regional training clusters and we do merging to combine the regional and global code. prefers studying minimal on purpose to preserve until more quickly to make it a useful research. Okay, so pre-training question covered. Let's talk about evaluation. This is sort of tasting your dish and whether it's good. If you don't have good taste buds, you can't decide if your model is good. So we took a very different philosophy to this model that is when it came to Viraat. To track development on languages, lots of people just do an average over the eval windows. Instead of doing just an average, look at different parameters. Look at your minimum energy. Look at your fluency. Look at your instruction forward. So choose very carefully what you want to measure to achieve, how you're measuring your language. For benchmarks, lots of people do multi-choice question answer. It's just saying A, B, C, D, and usually it's a log likelihood of this, and it's not even testing if you're able to generate in the language that you say. So instead of doing MCQA, do generative tasks. They're harder but more realistic, and they match to saying what the model is being used. In terms of metrics, lots of people look at accuracy only, but let's use other ones. And I said naturalness, instruction following, measure mean as well as the average. The other issue when it comes to evals is all of the evals will not cover all the languages that you're supposed to. We have 70 languages, not all. There's two ways to expand it that we use. One is we translate we take translation and use that to change the prompt from our language to our and this is sort of automatic, slightly imperfect. We spoke about we have a multi-state for that kind of thing. The second thing is to use a wide variety of benchmarks that cover overall your language itself. So we leverage both of these. So we have MRE Hard version 2 and we have, I believe, multilingual, which are both translated to 66 languages. Now, a common thing that we've used in the lab before to sort of measure generative performance is win rates. But the kids have three problems. They have high variance, so you can't compare generations even with different temperatures sometimes. Small stylistic changes will result in your judge flipping them. You can't anchor them. The rates are not comparable across different evaluations. And it's hard to interpret. You don't know why your judge chose this. And even if you do inspect it, it's unclear and it's inconsistent with us. So we came up with a rubric-based absolute. So we introduced a forward criterion rubric on a 7-point Likert scale. So we asked the judge to give scores on between 1 to 7 on forward accuracy, instruction following, coherence, fluency, and we average this and normalize it between 0 and 1, and we use that as a 5. This allows you to anchor each score has 1 to 7, so you can always compare maybe different modules and terms. If you have more interpretability, we prompt the judge to always explain its rationale, to forward scoring and giving validity. And the variance is reduced because you have 4 different criteria to score. So as an example, during early training, we found that Tanganyika was getting 90% win rates against Gemma 3. And the reason it was getting so high was Gemma 3 was not able to generate sentences in bench. And Tanganyika was just being given the win because it was actually able to generate a sensible sentence. But it might not be the correct answer to the prompt. So it was very hard for us to actually make progress without using win rates. So moving to this rubric-based scoring, you can inspect the judge prompts where it's saying this is my natural phase or this is well structured, some technical inaccuracy. So you can get a feeling for whether you're actually making progress on the particular language. Now, discriminative results. So we were aiming for a balanced performance, and so we did not actually chase after improving eval metrics on certain versions. So these are sort of like MCQA on a lot of different languages. Global and we include Kika, the 3 discriminated evals that we have. And the current 3 is equal to family leads on these benchmarks. And Tanganyika is not far off. And we can talk about in the next slide how we sort of see the balanced nature of the decisions that we're making and where we so yeah, like I said, we do not specifically target these benchmarks. These are all measured by not likelihood, so it doesn't even check if you're actually generating answers in the right language. And it's less aligned with our priorities and doesn't provide signal on whether you're improving generative performance for a given time. Now, for generative results, this is sort of where Tiny AI really shines, and this is from all the decisions that we made throughout. In multilingual doubling, we have +9 points over Gemma, +20 over Quen. But if you look at the standard deviations, which are the red numbers here, you can see that given this in this 66 language cluster, Gemma has like 25 points swing. So the worst performing language is 25 points off your so the standard deviation, probably low. Whereas for us, you see the standard deviations are much higher. And so this shows that we have more of a balanced performance across different variables, both on this cognitive and those our sessions. For Marina hard, Quen is better than us, even though it has a much higher standard deviation, and that's because we don't focus. Marina hard is more technical code style prompts, and we don't really have a strong focus on that than this. Okay, so the other thing is this chart. I really like this chart. So the yellow line here is telling you the number of pages for that language or language you think prompt for, and it's an exponential some axis there. This is the open-ended generative quality. These are sort of based on how much web data it is. And you see that the drop-off for Tiny AI, which is in green, is not that high. So we've tried to achieve this balance performance, and you can see that it's up east. And you can see for the other models, so Java does pretty well. But the other ones, there's a real drop off with the amount of data that's in. The other thing is when we include a bunch of translation data, how does Tiny AI do as a translator? And you can see that it's pretty strong. It actually matches and beats Gemma 4B, translate Gemma 4B, which is specifically trained to be a translation. Finally, for evaluations, we prioritize multilingual safety and in sort of against competitors. The mean safe rate actually looks pretty comparable. Maybe if you take out smaller left and construct Quet and Gemma comparable to Tiny AI. But when you look at the mean, that is the lowest language in the 10 languages that multi-jail, which is a jailbreak benchmark. You'll see like patterns like 1 point. It basically doesn't get really sensible into that. And it's very good. The other thing is like sort of merging so before and after merging with the global model, like the safety sort of characteristics transfer. The other thing is like I was having a discussion is how do models capture cultural nuance? How do they understand what they mean? And so there's some benchmarks here, and we wanted to see what that looks like. We didn't specifically solve for it, but it's required. And you can see that Kenya is okay across the different points, with COT and without COT. But what's interesting here is if you want to understand, let's say, Telugu culture, and you prompt it in Telugu, you'll get a worse answer than if you prompt it in English. And this is not just a problem for Tanya, this is across all the models, and it's very interesting that it's happening. There's a few reasons. English is the dominant language in which all the facts are present. So the models are really good at retrieving facts. And when you prompt them in English, they're going to give you much. And so all models perform better when prompted in English versus that way. So even at a glance, we're reading on the long tail of macros, particularly African mods. We're reading in translation tasks, competitive and open areas, strong in generating target language and answer responses, not as competitive in coding and sort of technical tasks, less competitive in discriminative tasks. But these are all the priorities. At this model scale, of course, you have hallucination and factual accuracy in others, English comprehension to but those are mostly addressed by scale. I'll quickly talk about on-device requirement and how multilingual performance changes depending on the price. So we adopt GGUF to do quantization. We do four quantization schemes: 8-bit, 4-bit, and use 4-bit. And we find that mixed 4-bit is solver the best performance for your sort of memory use. And we study the degradation. So when you use quantization, how does it get for different languages? So for high resource languages, the degradation is minimal. But even for low resource languages, even if you do it for bit quantization, degradations are really set. So it's a very viable strategy to do this sort of quantization and get a model that you can deploy create many types. So the final thing makes decision is about programs and the director will go into some UI form at 10 go. This was minimum. Okay. Share with you. So I will talk a little bit about the takeaways. So not just for multilingual, but if you're training a model, you really want to ask what is the purpose here, and what are your goals, and make sure you're incorporating that at every stage of your training. So balanced multilingual performance is a design choice. Your equity starts right at the tokenizer. And so you need to be thinking about from tokenization to your training, post training, strategy. No single features, but Fusion is much better than Curate design. Merging is very, very cheap. You already train the models, it's very powerful and acts as a very good readiness. And I can sort of attest to its power not just for multi, but across different modalities and then don't look at just the averages. Look at your variance, look at your means, look at your analysis. So in terms of what's next for Kenya, the quality still lags behind other ones in JavaScript like math and coding, and this was intentional, but I think we can still do better. Several languages will start. There's thousands of 77,000 is the last language. And so 70 is small. Hopefully we can increase this coverage while maintaining performance. English still performs other languages. Not super surprising, but something that we can improve on. And we have an older physical way that's from focusing on one thing. There's some maybe more data that we figure that out. But again, balanced material performance at a small scale is a design. You don't want to just build and really make. Think about it. Think about your choices at each stage. As you get hopefully come on in here and there. Sorry. So I want to talk a little bit about the history of art. And so like I've presented this talk about all the choices that we made. And we gave this model over minutes. But like you could trace back to January 2023 when we started the iPod. And this model is sort of a culmination of this one, I1 where we use translation as a synthetic definition. IR expands where we did sort of heavy rest event sort of synthetic definition. And each stage when we did this, we were reliant on sort of an external. IR101 was based on 25, was a base number that had other IR expands was based on an internal Cohere environment that had 23 languages that it issues. And so we couldn't go beyond. So TinyIO, we addressed the whole thing from the tokenization stage right till the test. And just a little bit about what we expect to do out of this. So this is a small 2-week sprint that we're having with this model where we invite community members to come build on this model with minimal compute and minimal resources. And I found this is our second edition of this, and it's sort of amazing to see what the community can do. But given a model like this, with not a lot of resources and not a lot of time. This is a 2-week sprint. Last time I believe it was 4 weeks. We had 5 to 6 papers, 2 of which were published at pretty prestigious conferences that came out of this. And so this is like a blueprint to accelerate the research output of your models and tools. Finally, I want to take a second to sort of acknowledge the third key and also thank them for explaining the large portion of these slides and a bunch of support at Cohere from such inputs. I think that's my part.